To harden is we want to get our metal as hard as we can, and then we need to temper it. We need to back off that a little bit. It's like stepping on the gas to get on the freeway, but then you got to back off that a little bit to maintain your speed or you're going to crash. Metal can have a hard that is brittle or a hard that is strong. We want a hard that is strong. We don't want a brittle, cracking type of hard. So our goal again is a tool that will last, and that means we need to get it in its most durable state. And we want to take every advantage of using that tool steel, that higher carbon with other additives, those hardness properties. We want to take every advantage of that. And hang on, I got a little, well, that's okay. So if you don't heat treat, if you don't get the steel to its hardest state, you're going to find that it fails quickly. And again, don't just take my word for it. Do a test, make a tool out of 4140 and then use it and see what happens to it. Very quickly within use, you're going to find that it fails. So our job is to investigate how to find and keep it in the hardest state possible. And luckily, our chart contains that information. And the state of being is another metallurgist word, and it's martensite. And if you haven't guessed already, or at least I'm assuming, someone with the name of Martin, which is again a word you do know, figured this out. So martensite, what does our chart say about martensite? And they have a little, there's no numbers over here, but it has some verbiage down here for us to read. Martensite is the hardest of the transformation products of austenite. And it's only formed only on cooling below a certain temperature. And that cooling must be sufficiently rapid. And why they use the terms sufficiently rapid is because that all depends on what kind of metal you're using. So we already know that we got to take it to austenite to normalize. We now want to prevent what we just did by cooling rapidly instead of letting it cool slowly. And another way to think about this is you can only get to martensite, the hardest, through austenite. And we just learned that austenite is achieved by taking the metal to that transformation temperature and cooling it rapidly. The softer state happens when we cool slowly. So to harden, we're really saying make martensite. So let's blow this up again, and we got to get it to that upper transformation temperature. And it's the same one we used for normalizing, and we want to freeze it there. When the metal is in its austenitic state, when you've got it in that high enough temperature, which for 0.4 carbon is right here, right in this 1500, 1600 range, the atoms are moving about, and that allows the carbon to insert itself between the iron atom structures. And when you cool it fast enough, you lock that carbon in and you create this hard interlock structure, like think frame for a steel building. And since time at temperature is a factor, we need to let it soak there, but for not too long, because the time and the hotter you get it, the bigger your grains are. We want small grains. Cracks have a hard time following along small grains. They have an easier time following along the larger grains. So how long do we soak? The rule of thumb, 5 minutes per inch of cross section. I already told you we're using 3/4 of an inch round. So we're less than that, less than 5 minutes. So in blacksmith terms, soak it a little bit. So our steps for martensite: heat slowly to just above that 1500 or 1600 degrees and quench it sufficiently rapidly. For 4140, you can use oil or water. I'm only calling out water here on the slide because it's easily available. You have it in your quench tank and you can avoid the messy, stinky oil fumes. The only time I would recommend you move to oil, which is a little slower quench, would be if you got something really thin, and we're not going to have anything that thin. And again, at the atomic level, what has happened is that carbon was captured inside those iron structures, making wedges that interlock all together. And this is a photo. I showed this in that basket handle talk with a lot of welding. This is a magnified view of a cross section of the weld. Here's the weld. And you can see these sharp needly things. That was martensite. That's an interlocked structure. So if that helps you visualize what's going on, that's what it looks like under a microscope. So we now have martensite. Oh, and let me point out that if you have a different steel, this is a different recipe. So this is just for the 4140. So we now have martensite, and this state or property makes it hard. But that captured carbon, these needle light, they even look kind of tense. We've got a lot of pent-up energy in there, like a pressure cooker or speeding your way onto the freeway. It needs to be backed off or released quickly. And I'm talking like the same day. You have to release this pressure you just created. And you can do that by a process called tempering, or the metal, the tattletale, will do it for you by cracking. So those are your options. So what is tempering? And we really want tempered martensite. Martensite is the hard stuff. We want to back it off. Tempered martensite. There's nothing else hard like the martensite. So over the years, this bit got left off, this phrase, tempered martensite, or this descriptor. And as I highlighted here for you, people just call it temper because you can only temper martensite. So what is tempering? Tempering is the act of reheating your tool enough to see colors on the outer layer. And what's happening there with these colors on the outer layer? When you expose the metal, in other words, you grind off all the oxides, usually with, I have some broken grinding wheels that I hold in my hand, just make sure you don't burn your hand. You can shine it up and remove all that oxidation. It's then reheated, and as it gets exposed to the air, the oxygen, again, it reacts to that oxygen and oxides return, causing a prism-like or refraction that your eyes see as colors, just like you'd see on a rainbow. So the color we're looking for is this straw color. Straw color right here, darker straw at 4040. So the steps to temper: shine a piece, reheat until you see that straw color. And you can do that in an oven. The temperature we're looking for is 430 degrees. And in an oven, you can get to 430 degrees, put your piece in for 15 minutes for every 1/4 of an inch wide. Or we put the two steps together with one heat, and we heat our piece up past the transformation temperature. We quench it, and then we shine it up, watch the colors run. And just just because it needs to be said, 1 out of 8 people are colorblind and might not be able to see these colors. So if there's someone in that category in this room, which is likely, there's a lot of us, you just need to get yourself a pyrometer or get one for fun if you want to be really clear on what color your temperature is, and look for 430 degrees right in between these two. So here is our blacksmith heat treat, harden, and temperature. Get your piece up to that upper transformation range to make, and I wish you were all like, I could hear you all right now because I'd want you to say it with me, Austinite. The chalk bit is for you to see that this top line is never in the water. The middle bit is in and out of the water. We don't want to make a stress line anywhere in here. We want to move it in and out. And that's what these arrows are about. We want to move it in and out. So we have grades or shades of stress. And then the tip is never out. That's the bit we want to harden and we want to cool. We want to get that sufficiently, we want that cooled rapidly. So when you quench, when you bring this, you've got it up to your austenite temperature, you bring it out, you quench it. The first thing you're going to hear is a hiss. And that hiss is the steam forming, that because you've just put really hot stuff in water. That steam creates a little vapor jacket around your metal, which will take the sufficiently rapid out of your sufficiently rapid. So you've got to agitate it. That's this moving in a figure eight or side to side, anything to kind of swish off that vapor jacket. And then you're going to go up and down to create gradients of stress, not just one stress line. And I usually find it's about, in and out, a count of 10 or 12. But what you're really looking for is the hissing to stop, or that the water no longer evaporates off that tip. Now we want to bring our piece out, set it on a steady surface, scrape it off, and watch the colors run. Now I'm showing an anvil here in the background. If you set this, we want the heat from here to travel down the edge and color our tip. If you set this on the anvil, the heat's going to find that big heat sink very attractive. So you want to make sure that you're holding this off the edge of the anvil. Maybe only the tongs are touching the anvil, so that your heat is attracted to this cool part, newly cooled part of your tool. You're going to see the color, that straw color, start to travel down that tip, and then you'll see the purple and the blue following closely behind. If the colors run once, that's great. You got once. But if you have enough heat left, do it again. Hit that back in this bucket just once this time, because you already cooled it once. We're only at 430 degrees. So quench that, bring it back out. Be careful not to have your anvil act as a heat sink by holding it off the edge, scrape off that edge, and then watch those colors run. If you can run those colors once, great. If you could get it done 2, 3 times, even better. Every time those colors run, you're moving closer and closer to smaller, or you're making smaller and smaller grain structures. And your test for this is a file. And your file should meet with some more resistance. So here's a spot for questions, if anybody has any. And I don't expect you to learn the language of the metallurgist in 1 or 5 goes, or even 10. What I do want you to understand is how to heat treat so you can do it safely, and that and I want you to know that what you're doing is you're capturing the state of being, or the property that makes your tool durable.